Hey guys, it's been a while. Coming to you today with a little bit of a different video. So it is currently raining outside and I now have to be cooped up in the house all day long. And so I guess I wanted to go ahead and take this opportunity now to make this video about something I've been working with off and on for the past couple of weeks or so, related to the Rubik's Cube and twisty puzzles in general, about counting reachable positions based on applied moves, and how it actually led me to some pretty cool new discoveries and proving a new lower bound for the God's number for the face-turning octahedron, which is now at 21 moves. So this video is going to be showing how I did it, and more or less a walkthrough of my entire thought process and how it developed over time. This video will most likely be in 3 parts, the first being an introduction to the basic concept of using simple permutation counts of the Rubik's Cube to approximate its God's number, and the second being about my improved logical method I came up with and the amazing mathematical patterns that it revealed, and third for generalizing to other puzzles including the FTO and demonstrating the brute calculation needed for bounding God's number. So let's go ahead and jump right in. We'll go ahead and start with thinking about the regular Rubik's Cube, because that's what everybody is mostly familiar with. And so the initial idea that I really had for doing this whole thing was I was just thinking about, when you start with a solved cube, you can do moves sequentially one at a time to scramble up the cube and mix it up. And this allows you to reach all of the different positions or permutations of the puzzle. And it's been known for some time now, in fact just about a decade, that any Rubik's Cube scramble can always be solved in 20 or fewer moves in half-turn metric. And that is known as the God's number of the puzzle. And so that means that no matter how it's mixed up, there is always a solution that is going to take 20 or fewer total moves. And this is not it. Alright, so yeah, back to solve now. So what I wanted to think about was, is there a way to sort of track how many positions that you're able to reach after doing a certain number of moves, saying doing one move and then another move, assuming these moves are, I guess, sort of random, or that you can pick any move you want. I was trying to think about, how many positions that would be reachable with that many moves. So how would we be able to sort of calculate and track that? Well, here's one way that we can think about it. So starting off with a 3x3 cube, we can sort of think about what our choices are for each subsequent move. So if we're starting with a solved cube here, and we make our first move, how many possible first moves can we do? Well, on a cube there are 6 layers that we could choose to make our turn, and for each of those layers, there are 3 possible directions. We can turn clockwise, or counterclockwise, or 180 degrees. So if there's 6 layers and 3 choices for directions, then that means that for the first move, there are going to be 6 times 3, or 18 possible first moves. And this is pretty obvious to think about. Those moves could be something like R, or F2, or B prime, and etc. But now what if we go on and then make 2 moves? We could argue that your first move is again going to be one of 18 possibilities, and then your second move can again be move on any layer in the same sort of way, so then that's also going to be again 18 possibilities, and that answer is going to be 324. So that means that there are 324 ways that you can make 2 moves on the cube. Unfortunately, this is wrong. And what is the mistake here? Well, it has to do with the fact that after we make our first move on the cube, let's say we do an R move, then the second move that we make should actually be on a different layer, right? We don't want to make R and then R2 after that, because that's a cancellation. Those moves would be able to cancel into each other. And we don't want to do anything like that, because this is an example of a position that's actually just 1 move away, not 2. So if we want to really accurately capture doing 2 different moves, then when we make our first move on one layer, we need our second move to be on a different layer, as you can see. So if we have 18 choices for our first move, that means for our second move we had to pick a different layer than the one previously, and that means that there are only 5 possible layers we could choose with 3 directions, which is 15 choices. So to fix our calculation here, we need to change that second number to be a 15. So now we have 18 times 15, and that's going to give us 270 positions. Now, very unfortunately, this is actually still not quite right. If we're trying to capture the number of possible permutations that we can reach with 2 moves, then 270 is still not the right answer. If you look at cube20.org, which is the website that has all the information about proving the God's number for the cube being 20 moves, there is a little chart that will show how many positions can be reached with a certain number of moves. And you'll see that the correct answer for 2 moves is actually 243. So where does that number come from? And why was our calculation not quite right? Well, it's ultimately due to the fact that the 3x3 cube has actually 2 types of layers. It has layers that are adjacent to each other, but it also has layers which are opposite of each other. So for example, if we do one move on one layer, as our first move, let's say, and then let's say our second move is an adjacent layer, then that doesn't create any issues, right? The order does in fact matter as for what permutation you get. But if, let's say, you do a move on one layer and then your next move is on an opposite layer, this is actually a different situation, right? Because these 2 layers don't mix with each other, they can commute, and in fact, the moves can be done in either order. So we can do R, L2, or L2R, and it turns out to be exactly the same position. So in other words, this 270 number is actually counting these positions too many times, and we need to account for that. So how do we have to modify our answer here? We're going to have to change that second number, but in what way? Well, we can think about splitting it into cases. So if we pick our first move, and let's say that's just an R move, then the next move has 2 possibilities. It's either going to be made on a layer that's adjacent to the first move, or it's going to be made on a layer that is opposite of the first move. Now for all of these adjacent layers, there are 4 of them, and again 3 choices for the direction, as we've mentioned before, which means there are 12 possibilities if the second move is an adjacent layer. But if our second move is an opposite layer, like let's say an L move of some sort, then there's only 1 possible layer that's opposite, right? Each layer has only 1 opposite layer. And then again, we can turn that layer in any of 3 directions, so there are 3 choices if the second move is an opposite layer. So let's split up those cases here. Breaking the second move down into categories, again, we have 2 possibilities. It's either going to be an adjacent layer or an opposite layer. Now there were 12 choices for an adjacent layer. And remember, there were no things that we had to account for in that situation. Everything still works normally for adjacent moves. So that's going to be 12 possibilities like we just went over. And then for the case where we have an opposite layer as our second move, there are going to be 3 choices. But remember, the order in that case didn't matter. And so we actually can do either one of both orders. The first move or the second move can actually be exchanged as the first move. So we have to take this number and divide it by 2 to account for that. So now, finally, doing this calculation, we do in fact get the correct answer of 243 positions. So if this is already getting a little confusing for you, keep in mind that we've only scratched the surface here. We've only just done 2 moves and 243 possible positions, when in reality, the Rubik's Cube is possible of a total of 20 moves and reaching all 43 quintillion. So it is absolutely not a trivial problem to count the number of permutations based on the number of moves you make. There are a lot of little nuances as we've seen here, and that's what makes figuring out the God's number for a puzzle so difficult. But now wait a second. How can we actually use these calculations to help us bound the God's number? What helps us knowing the permutations reachable with a certain number of moves? Well, the thing to remember is that the Rubik's Cube, and in fact any doctrinaire twisty puzzle, has a finite number of total reachable permutations. In other words, we can tally up as we go along how many moves we have done on the puzzle to see how many permutations we have passed through in total and see when it exceeds that finite bound. So let's just say that the number of total positions that we reach with a certain number of moves. Let's go ahead and call that T for the lack of a better name. And then let's say that the total number of permutations that are reachable, let's go ahead and call that P. So if we go along and tally up all of the permutations that we pass through as we do 1 move, 2 move, 3 moves, etc., and keeping track of how many moves we've done, once T surpasses P, in other words, we've maxed out our permutations, then we know that however many moves it took to reach this point, that number of moves is going to be a lower bound, G, for the God's number. So in other words, if we're able to approximate the number of permutations that we can reach with a certain number of moves, even somewhat well, then we can also approximate what the God's number of the puzzle is going to be. We know that there has to be a lower bound for the God's number. In other words, we'll be able to find out that there are certain positions that have to require this many moves to solve. There could be other positions that require more moves to solve, but if we can just show that there exists some of them that require this many moves to solve, then that's a lower bound for that total God's number. Now, a very simple and naive way to do this calculation actually quite quickly is to take this second factor that we had for our second move and use this number to more or less approximate how the number of positions grows as we do more moves. So if we set up some algebra and do some quick math and rearranging, which I will skip to the end here, then we can actually approximate the God's number as being equivalent to log base our branching factor, which is this second term here, of the number of total permutations. And for the Rubik's Cube, this gives us a total of 17 moves, which is actually pretty good. You know, the actual God's number is 20 moves, and so 17 isn't too far off. But remember that this is only an approximation. Simply using this branching factor right here is only going to approximately count the number of permutations we go through. As we know, the true answer is going to be slightly different, and these factors actually do change over time as we start going through more moves. So this is not a constant number, but by pretending that it is, we can still do pretty well. But at this point, you know, I wanted to try applying this to the FTO, and I really got to thinking about, is there any way that we can do better? Is there a way that we can approximate these permutations any better? And I did discover a way, and it revealed some pretty interesting results. So let's go ahead and take a look at that. So I thought about all of this quite a bit more, and I realized that if we think about everything in terms of pure logic and conditional cases, then all of these calculations can actually be boiled down to just using 2 rules. So let's take a look at what those are. The first rule is that any 2 adjacent moves must be made on different layers. For example, a sequence like R, R2 would not be allowed. And we've already seen this before, of course. If you make one move on one layer, then your next move must be made on a different layer. This rule is pretty obvious, and implementing it into the calculations changes each factor and makes it more accurate, as we've seen before. Now, the second rule is a little more interesting. If we make 2 consecutive moves on opposite layers, then the third move must be made on an adjacent layer. So a sequence like R2, L, R prime would not be allowed. Again, as we've seen, if you make one move and then another move, then they're on opposite layers, we can exchange the order of those moves and get the same result. So we could swap this R2 and L right here, and then the R2 and R prime would be able to cancel with each other, and therefore they commute, which is not something that we want. This second rule was able to fix our calculation for 2 moves, as we saw, to bring it down to the correct answer of 243. So this is a very important rule and makes our calculations a lot more accurate, especially with the early numbers. Here's an example of a legal move sequence that totally works. You can see that it follows our rules. After any move that we look at, the next move is on a different layer. And if 2 moves are on opposite layers, then the third move is on an adjacent layer. So this is an example of one that works. And I'll go ahead and leave this on the whiteboard so that we can have it for reference. Now, what I noticed that is quite interesting about these moveset rules is for this second one, This is actually a conditional statement. We first need to have two adjacent moves that are on opposite layers for the second rule to even be applied in the first place. So for a conditional statement like this, I realized that we could actually draw a logical network of all of our possible ways that we could have our move sequences written down, and therefore our reachable permutations. Keep those two rules in the back of your mind though, because those are very important for what we're about to do next. So now, the first thing we really have to do here is make this extremely generalized. We're going to assume that the moves that we make could be any moves at all, and so we really need variables to represent these moves. So what I'm actually going to use is the Greek lowercase letters to be placeholders for our moves, but really they represent any moves that we make on the regular 3x3 cube, so just the standard 3x3 cube notation. So let's say we start off with our first move, which I'm just going to denote with alpha. So again, just our Greek letter to be a placeholder there. Now, as we saw previously, there are 18 possible choices for this first move, and that's because this is the first move, so it doesn't really have to follow any of those rules that we laid out previously. So we'll go ahead and write the number 18 above this move to indicate its possible choices. Also, this number represents the number of permutations that are reachable with just a single move, so that's another way to look at it. Now what we'll do is we'll move on and say that we do a next move, which I will just draw an arrow to indicate that we're kind of moving along our sequence of moves that we make here. So our next move I'm going to call beta, and this is where things can actually get interesting, because now that we have two moves here, we now have to follow both of those rules previously. With this second move, it cannot be on the same layer as the previous move, so that automatically knocks this second move down to only 15 choices. But remember that we also have that second rule that we have to follow, that conditional statement, that says that if these two moves are on opposite layers, the next move has to be on an adjacent layer. So there are really two possibilities for this second move. This second move is either an adjacent layer to the first, or an opposite layer to the first. So this has multiple choices, and therefore we want to split this up into the multiple possibilities that it has. So we're going to draw two arrows that come out of this second move here. One of these possibilities is that this layer is adjacent to this layer, in which case there are 12 choices for this second move. So that's what I'll pick for this top arrow here. I'm going to say that this has a total of 12 possible choices. And then for the second scenario, this second move is on an opposite layer to the first, and there are only 3 choices for it. So that's going to be reserved for this bottom arrow here. We're going to say that this one is that case, and there are 3 possibilities. Now we can continue to logically draw out our path. Now I'm only going to go up to 4 moves, but keep in mind that this should be able to go out to any number of moves that we want to make. So now let's think about what happens with each possibility. Let's say that we start with that first one on top, in which case these 2 moves are on adjacent layers and there are 12 choices for that second move. So now we can go on to doing a third move, and I'm going to denote that move with gamma. So now, what are our options for this third move? Well, the previous moves were on adjacent layers, so it really doesn't matter what's going on with this third move here. It again has to follow the first rule, but not necessarily the second rule, right? Because since these 2 layers going this direction are adjacent, then we don't even have to consider that second rule, and we can just do the same thing that we did for the previous move. This has a total of 15 possibilities, but 12 of those are going to be an adjacent layer, and 3 of those are going to be an opposite layer compared to the previous move. So again, we'll draw 2 arrows out of this move, indicating those possibilities. Again, the first possibility is that it's an adjacent layer move, in which case there are 12 choices, and the second possibility is that it's an opposite layer move, in which case there are 3 choices. So you can see that it's exactly the same as with this second move here. So that's not too interesting, but let's see what happens in the second case for that second move. So for this case down here, the second move is on an opposite layer compared to the first move. So what are our choices going to be for the third move this time? Well, remember that this possibility is that these 2 moves are in fact on opposite layers. So that means we have to apply the second rule here. And the second rule says that this third move that follows must be on an adjacent layer. It cannot be an opposite layer move. So therefore, there are only 12 choices for this move, and that is it, nothing else. So we have no freedom of choice here, and there's only one possibility. So this third move this time is only going to have 12 possible choices. And then we simply move on from there. So now we'll go ahead and add in our fourth moves, which I will call delta. And there are 3 places where this goes. And now we can work out the possibilities for each of these. So let's start back up here again. Let's say that we look at this very top delta over here. If we look at the path that we went along here, the previous move was on an opposite layer compared to the second move, as you can see, because this path is labeled with a 3. So therefore, there is no free choice with this fourth move, and therefore there are only 12 possibilities, and there is no way to choose between 12 or 3. So this one is going to have to be 12 up here. Now let's look at this second possibility for the fourth move. So for this one, as you can see, we came from a choice of 12, which means that these 2 moves were on adjacent layers. So for this one, it doesn't matter. We can choose whichever one we want, whether it's an adjacent layer move or an opposite layer move. So now this one will have 2 arrows that come out of it to indicate those possibilities. The first case is again that it's an adjacent layer move, in which there are 12 choices, and the second case is that it's an opposite layer move, in which case there are 3 choices. So it's basically the same sort of thing that we've seen already. And now for this bottom one, I'll leave it as an exercise to you, but it should be pretty obvious to figure this one out. We have 2 choices. So here, this is it. We have our logical network that basically illustrates all of the possibilities that we can choose for our 4-move sequence. Each path that we move along represents a different choice for adjacent layer moves or opposite layer moves in the sequence. Again, the first move can be absolutely anything, but the second move could either be an adjacent layer move or an opposite layer move. And then based on that, we have a certain choice for our next move, and then after that we can have choices whether it's an adjacent layer move or opposite layer move as before. And so you can see all of these possible combinations really give us all of the possible ways that we could apply 4 moves to the cube. Alright, so this is fine and all, but what the heck? How does this actually help us? How can we actually use this network to calculate the number of permutations that are reachable for any certain number of moves? We can just step back for a moment and effectively realize that in this network, any path that we take to the very end represents a possible way that we could have our sequence of 4 moves. And each of these numbers represents our choices for that nth move, the first move, second move, third move, and fourth move, and so on. So all we have to do is simply pick a path and then multiply all of those numbers together that we have on that path. So let's say we pick this very first path going this way. So we go through 18, then 12, then 12, then 12 again. So for this type of sequence, we're only making adjacent layer moves every time and no opposite layer moves. So for that first path, we have 18 times 12 times 12 times 12 possibilities. So if we calculate that out, that gives us a total of 31,104. So that's great, but remember that this is only one possible path. There are multiple paths in this picture, and we need to account for all of them. So, in other words, in order to get the total number of permutations, more or less, that are reachable with 4 moves, we just need to consider every single possible path that we can take in this network. For each path, multiply all of the numbers together, get our answers, and then add up all of those answers for each path. And that should give us the total. But there's actually one other rule that we have to apply for these calculations, and I'll illustrate it with one more path here. Let's say that we pick this path here where we go from 18 to 12 to 3, and then to 12 up here. If we calculate this out, then that's going to be 18 times 12 times 3 times 12. For this path, the difference is that we have a factor of 3 in here. And remember, when we have a 3 that pops up, what that's really saying is that we ran across a case where 2 moves were done on opposite layers. And remember way back when we had to do that calculation previously with that 2 move case and we had to divide that number by 2? Well, it's the same thing for this. We're going to have to divide this whole product here by 1 factor of 2. So for every single factor of 3 that shows up in our product, it means that we had 2 moves that were done on opposite layers. And anytime we have 2 moves done on opposite layers, that means that we're going to have to divide that answer by 2 to account for the fact that those moves can switch over and be the same position. So effectively, we're removing all of those extraneous positions that we accidentally counted too many times. So by doing this calculation, we get 3,888. So that's all we really have to do here. And let's actually see this work in action. I'm going to do the example where we actually only have 3 moves instead of 4 moves, because 4 moves takes a little bit of time. And also I just want to illustrate a couple more things. So we're going to take this network and we're just going to pretend that the delta doesn't exist for a second. That 4th move doesn't exist. And we'll go ahead and do the full calculation. So let's see what we get. So for 3 moves, we have a total of 3 different paths. So we have this one here. We have this one here, and we have this one here. And that's it. Remember, we're ignoring the deltas, so those paths that come out of the delta don't matter, that come out of that 4th move don't matter. We're only going up to the 3rd move, which is gamma. So our first path is going to be, let's say, from 18 to 12 to 3. So that first path is going to be 18 times 12 times 3. Oh, we hit a factor of 3 here. So we have to divide this product by 2, and that gives us 324. Great. So that's the first path. Now let's take a look at the second path. So let's say the second path is going from 18 to 12 to 12. So that one's going to be 18 times 12 times 12, and that gives us an answer of 2,592. All right. And now we just have one more path left, the 3rd one, and that's the one that goes towards the bottom here. So 18 times 3 times 12. So that one's going to be 18 times 3 times 12, and then we have a factor of 3, so we have to divide this one by 2, and that's going to give us the same thing from up here, 324. So these are all the possible paths for 3 moves that we can have. And now to get our final answer for how many permutations can we reach with 3 moves, we just need to take all these numbers and add them together. And if we do that, we get an answer of 3,240. And actually that's correct. If you take a look at Q20.org's chart, you'll see that at a 3-move depth, we reach 3,240 permutations. So this is awesome. Even when we go to 3 moves, we're still getting the exact answer. So this is a very accurate way to count permutations, which is exactly what we want if we want to really improve the God's number lower bound for our puzzle that we're looking at. So that's great. Now let's move on to using the entire chart that we've drawn here. So we'll go to 4 moves. And I'm just going to put down all the calculations really quickly. I'm not going to bother illustrating them too much. So you'll just see it on screen here. Now for 4 moves, we have a total of 5 different paths. So let's go ahead and write these all out. Now for this last one, notice that we have to divide by 2 factors of 2 because we have 2 factors of 3 in our main calculation. So now I'll save you from doing all the number crunching. If we add up all of these numbers together, we get a final answer of 43,254. Wait a second. That's not correct. If you look at the chart, it's actually supposed to be 43,239. We have an extra 15 positions in our number that we found here. So what went wrong? Well, the answer is that even with these 2 logical rules, this is still not quite enough to capture all of the cancellations that can happen when you do moves on the cube. You see, when we go up to 4 moves, something else starts to happen. There are certain permutations that can be reached in multiple ways that don't account for those first 2 rules. Here's an example of one of those. If you do R2, B2, F2, L2, this 4 mover can actually be reached in another way by swapping the outer 2 moves. So you can actually do L2, U2, D2, R2 and still reach that same position, as you can see here. But our rules didn't account for that kind of cancellation, and so ultimately, with our rules, we're still not canceling out everything that can possibly happen. Another 4 mover that can also cancel in multiple ways is this one, R2, L2, B2, F2. So these are 2 permutations that can be reached with multiple ways that we didn't account for. And in fact, it's for that first one, there are 2 ways that you can reach this one, so we overcounted it twice, but then there are 2 symmetries of this position. It can either be this way, or it can be this way. And there are a total of 3 axes on the cube, so that actually means we've overcounted that position 12 times. And then for the R2, L2, B2, F2 position, there's 1 extra way that we accidentally didn't account for. And there are 3 axes, so there are 3 of those, which means a total of 15 4 movers that we have accidentally counted too many times. And so if we subtract 15 from our answer over there, we would see that we would actually get the correct answer of 43,239. But this is still incredibly accurate. As you can see, we were only 15 off. And it turns out that this logical network method is in fact extremely accurate. Even if you go up to 10 moves, you only get about 5% error, which is very good. So we can actually use this to our great advantage to be able to figure out permutation counts for X number of moves and apply that to help us find lower bounds for the God's number. So it might seem like that we're pretty much done here. We now have this way to calculate the permutations based on the number of moves we're doing, but in reality there's one major problem that we still haven't addressed yet, and that is, how do we do this generally? I mean, this network we drew here was for 4 moves, right? But we could add on as many moves as we want to and create an even more complicated network, but it's not at all obvious how that would extrapolate from here. So what we need to do is to find some pattern, some general formula of some sort that will actually allow us to figure out how to do each of these calculations for however many moves we're dealing with. In other words, we need some way to figure out how to make all of these products here and construct them so that we can add them together and get our final answer. Ultimately, this network, while great to see how it works, is really just a visual aid here. So I spent a long time again just thinking about what's really going on here, and I noticed that there are actually quite a few patterns that we can notice within any of these networks in general. And in fact, there are 4 specific statements that we can make about them. So the first one is that any path that can appear will appear once and only once in any of our networks. So if you see here, for example, this path of 18, 12, 12, and 12 only appears once here. There are no other paths that are 18 followed by 3 12s. Each path is unique. And the reason why we have that is because remember that with our moves, the order does matter, right? With each of these paths, we're starting with our first move over here at alpha and then working our way through the network until we reach the end of a path. So this is always our starting point, and we always reach some ending point every time. Also, another detail is that every single node, or effectively move here, has free choice for the most part. Of course, besides that one rule where if you have opposite layers that turn for 2 adjacent moves, then you have to pick an adjacent move, and there is no choice. But other than that, you pretty much have freedom of choice with each of these paths that you take. And there is no backtracking, so once we've moved across the path, we have to keep going and we can't go backwards. Or at least that's the rule that we're really following for this network in this case. So that's going to guarantee that every single path is unique and it will only appear once each time. The other thing that we can notice here is that for an n move network, there will be exactly n arrows or n numbers on each path. And that one's pretty obvious to see, right? Because since it's 4 moves long, you're going to be crossing over moves 4 times. And so you get 4 numbers from that. The third property with these networks is within the actual numbers themselves. And this is something really important to note, is that if we move along any of these paths of our liking, if we cross over, let's say, a 12, then the next number can be either a 12 or a 3. It doesn't matter. So if you cross over this 12, it's either 3 or 12. Cross over this 12, you can pick either 3 or 12. So whenever you cross over 12, you have complete freedom of choice for your next number. It's either going to be 12 or 3, and you can pick either one. There's no restriction. But if we cross over a 3 as we move along our path, then the very next number has to be a 12. As we said before, if you cross over a 3, it means the previous 2 moves were on opposite layers, and the next move must be on an adjacent layer, so there is no freedom of choice, and it has to be a 12. So in other words, we can sort of break it down like this. If 12, then either 3 or 12, it doesn't matter. But if 3, then 12. So you sort of have that conditional restriction with these numbers here. And it's a little bit of an easier way to think about, instead of adjacent layers, opposite layers, all your choices, it's, oh, if you hit a 3, the next number has to be a 12. But if you have a 12, it can either be 12 or 3, and you can pick whichever one you like. Now, in a minute, I'm going to write down these sort of product calculations a little bit more neatly and concisely so we can look at some of the patterns in these. But there is one more very unexpected and truly surprising pattern within these networks that I would like to show now. So to do that, I'm going to make some room over here on the right-hand side. So now let's take a look at how many paths we're actually getting depending on how many moves we have in our network. So let's just have one column where it's the moves, and then this is going to be the paths. So now we have this table here. And so now we can sort of go through and look at 0 move networks, 1 move networks, 2, and so on, all the way down. So let's start with, let's say, 0 move network. How many paths are we going to have in a 0 move network? Well, if there are 0 moves, there's only one network that you can draw, right? And that network is nothing. So you can say that there is exactly one path that we have. It's sort of a, I guess, metaphysical way to think about it. But this is sort of really counting the number of ways that you can have your paths. So we have one path for 0 moves. Now, what about for 1 move? How many paths are we going to have? Well, again, that's just like this, where we just have alpha right here and then nothing else after that. So it's just going to be 1. Again. What about for 2 moves? How many paths do we have? Well, that's assuming we only have 2 moves, so we have alpha and beta. And now we can count this, so we have one path that would go up here, and then a second path that would go down there. So that's going to be 2 paths. All right, and so we can continue this along here. So now for 3 moves, let's count the number of paths. We're going to have 1, 2, 3. So that's going to be 3 paths. All right. Now patterns might be starting to emerge here, but let's just go one more step. So for 4 moves, and that is actually how many moves we have in our network that we've drawn on this board here, let's see how many paths we have. Well, we have 1, 2, 3, 4, and 5. And I think you might already just start to see what is going on here. Something very interesting. And in fact, just to kind of continue this pattern one more time, if we continue this all the way down to 5 moves, I won't actually draw the picture or the network, I guess, for this, but I can confirm that you will, in fact, get 8 paths out of that 5 move network. So if you take a look at this second column, this is actually the Fibonacci sequence. Isn't that amazing? You actually get the Fibonacci numbers out of these networks that describe our move sequences that we're doing on the cube. And when I first saw this, my mind was absolutely blown. I seriously couldn't believe that something as unrelated as the Fibonacci numbers was showing up in doing calculations on the Rubik's Cube and twisty puzzles in general. It's really unexpected to see this, and at first it might bewilder you, like how on earth are we getting Fibonacci numbers from this sort of thing? And it does turn out that this is not random or an accident. There is actually a reason that we get the Fibonacci sequence when we count up the number of paths in our network, and that's what I'm going to show now. So now we're going to actually move along to creating the chart of all of our products from multiplying all the numbers from our paths. So let's take a look at that. So again, we'll start with 3 by 3 cube, and so that means we're going to be using the same numbers that we were using previously to describe each of the moves in our network, which are 18, 12, and 3. 18 describing the very first move, 12 describing the number of possible choices for an adjacent layer move, and 3 describing the number of possible choices for an opposite layer move. So as we've seen before, the first move is always going to be 18, so we can just kind of put that off to the side on the left here, and I'll actually do that first. Now what I'm going to do is I'm going to fill in some rows and columns. So each row is going to represent one path, and the number of columns that we have is effectively going to represent how many moves that we're looking at. So we'll actually start with 4 moves here. So I'm going to write it like this. I'm leaving out this empty space so that I can add in another column to illustrate something else in a second, which we'll see when we expand to more moves. So what are our possibilities? Well, remember from before, we can have as many 12s as we want, that's fine. But if we have a 3, the next number must be a 12. So our first option for our path could be all of these being 12s. Then another option could be 12, 12, 3. Then let's say 12, 3, 12. And now we can't do 12, 3, 3 because that would be a 3 followed by a 3, which is not allowed. We can only follow a 3 by a 12. So next we could say do 3, 12, 12, and then 3, 12, 3. And actually that is it. So if we're looking at a 4-move network, these 5 choices are the only 5 choices that we can do. And it makes sense that we got 5 rows, right? Remember, that was the number of paths that we had for a 4-move network. Again, 5 being the Fibonacci number. So, and then the rest of these can be filled out with 18, 18. So this is what we get for 4 moves. So now let's say we want to go to 5 moves. Well, we want to add in another column right here. And let's see, this is all going to be 12s. And now we're going to have to expand with some more rows below. So let's say this is going to be a 3 now, as you can see. And this can be a 12, 12, 12. Then we can have 3, 12, 12, 3. And then 3, 12, 3, 12. And that is it. Again, we have to stop here. There are no other options. We can't put any 3s in there in any other way because it simply doesn't work. Otherwise, we'd have 3s next to each other, and that's not allowed by our rules. And so let's go ahead and fill in these 18s here. And remember, for these calculations, what we're doing with all of these numbers is that we're multiplying them together across all of these rows. And the other thing we have to keep in mind for these calculations is that if we find a factor of 3 in these rows, then we're going to have to divide that product by that many factors of 2. So for example, here we're going to have to divide by 2, divide by 2, divide by 2. Here we'll have to divide by 4 because there are 2 factors of 3. Just by 2, just by 4 that time, and by 4 that time. So this is what we would really have for all of these multiplications. This is what we would get if we were doing the 5-move calculation. Then we would add all of that together and get, whatever the answer is for 5 moves. I don't know off the top of my head. So really what we want to do here is to somehow be able to extrapolate what we would need to construct for 6 moves or 7 moves or any number of moves. Is there some sort of pattern in the way that we can construct all of these products? And it turns out there actually is. Notice that when we went from 4 moves to 5 moves, we added 3 more rows here, right? So we added these 3 extra rows, And in these extra rows, this was always a 3 in that new column here. And these were always a 12 in this new column here. And this is always going to be true. And let's say we were going instead from 3 moves to 4 moves, so one step prior, then it would be the same sort of thing. This would always be a 3 here, and this would always be a 12 here. We would be adding this column. This is the sort of idea of expanding this matrix out further as we add more moves. But how do we actually fill in all of these positions? How do we know whether to put 12s or 3s? And how do we know if this is going to be unique? Well, what we can notice here is there actually is a very interesting pattern. So in our case, when we expanded from 4 to 5 moves, we added 3 more rows. And in these 3 rows, we know this is always going to be an 18 for this first column. And then as I had said, these are going to be 3s, these are going to be 12s. So in these 3 rows here, we have 3s. If we take a look at this whole section of 9 numbers right here that I have boxed in, if we look up, we actually already saw that previously. Take a look at this section here. Notice that these 2 sets of numbers are exactly the same. They're actually replicated. So in other words, for this new set of rows, all of these numbers that we have to fill in for here are all of the numbers from the start of the original matrix down to stopping before the previous rows from the previous stage. So this is sort of a recursive definition for this matrix, right? You can see that this sort of recursion pattern that occurs. And this actually does hold true. Even if we were to look at, let's say, the 4 move to the 3 move case, notice that this set of numbers here is the same as this set of numbers here. You can see that same sort of pattern. So this recursive pattern actually holds for every single new addition of columns and subsequently rows. So this is the pattern that we can use to our advantage here to actually be able to construct this matrix of any size that we want for any number of moves. We just have to sort of replicate what was there previously. Now, why does this happen? Why do we get this pattern in the first place? Well, remember how we got those Fibonacci numbers before? This is actually why Fibonacci numbers show up when we're doing these calculations and constructing these sequences. The proof of this is really cool, and you should definitely give it a try on your own if you feel ambitious, but here's basically the gist of what's going on. So again, the pattern is that for every time we expand by 1 more column and add the new rows, the square grid of numbers, effectively, that appear in that new set of rows is going to be exactly equivalent to everything from the start down to before we get to the previous set of rows. So that's the first thing to observe. The second thing is with our Fibonacci numbers, they themselves actually have their own recurrence relation. And that formula is that the nth Fibonacci number is equal to the sum of the previous 2 Fibonacci numbers. This is the familiar one that I think most people are familiar with, but there's actually a way that we can algebraically manipulate this a little bit. This f sub n minus 1, that is the previous Fibonacci number, can actually also be written using the same Fibonacci recurrence relation. We can actually split this up into f sub n minus 2 plus f sub n minus 3. Then we can take f sub n minus 2 and split this up into n minus 3 plus n minus 4. And then we can split up the 3 here, and we can just keep going down like this until we get to f sub 0. And f sub 0 equals 1, at least based on our indices. Remember, for 0 moves, we had 1 path. So you can keep going until you get down to the first Fibonacci number, and you can see that going all the way back up is saying that we are using every single Fibonacci number minus the very previous one. Because remember, this is the one that we split up to get all of the other Fibonacci numbers. So in fact, the regular old Fibonacci recurrence relation is equivalent to the recurrence that's going on with these matrices, and that is why the Fibonacci numbers show up with this calculation. So that explains that mystery, and this is still just so incredibly cool to me. It's just amazing to see that those two rules before, those logical conditional rules, actually produce the Fibonacci sequence and subsequent patterns. It's just amazing and unexpected to see that. Math is just really cool sometimes. All right, so how do we generalize this further? So all of this stuff here was for the 3x3 cube, right? All of these numbers, 18, 12, and 3, are representing the moves on a 3x3 cube. What if we want to generalize this to other twisty puzzles, such as the face-turning octahedron? How can we apply the same sort of technique with doing all of these recurrence relations and constructing these matrices and so forth, and producing our path, our network with all the paths and calculating all our permutations? How can we apply all that stuff to a different puzzle, say this one? Well, it's actually very simple. All we actually need to do is change around some of these numbers. Remember, the 18 was representing how many choices you have for the first move, and then the 12 and the 3 represented how many choices you have for a subsequent move, whether it's on an adjacent layer or on an opposite layer compared to the previous move. So those numbers for the 3x3 cube, those are 12 and 3 respectively because of just the way that the layers are structured and organized. But for an FTO, what are those numbers going to be? Well, we can still figure them out. If we do, let's say, our first move, well, on an FTO there are 8 layers, and there are only 2 possible directions that you can turn a layer instead of 3. So that would be 8 times 2, or 16. So for an FTO, we would need to change this first column to a 16. And then for the next subsequent moves, we would just need to look at how many layers are adjacent to our first one and how many are opposite. How many possibilities are there for a second move where it's an adjacent layer move? Well, we have 6 layers that are adjacent to our first one, so that means we're going to have 6 times 2, or 12 possibilities for an adjacent move. So actually the 12 would stay exactly the same for the FTO, but the 3 is going to change because if we look at the opposite layer on the FTO, there are only 2 choices for the direction, either clockwise or counterclockwise, so all these 3s would change to 2s. But honestly, other than that, it's exactly the same. We would just need to change around these numbers to incorporate the geometry of the puzzle, and the division by 2s, by factors of 2, actually still holds because it doesn't matter what the geometry is. If you have 2 moves that are opposite layers, then you're still going to have to divide by 2 because there are 2 ways to arrange those moves that you can have. So now let's finally go over to the computer and actually code this stuff up, actually do the calculation, and get our answer for the God's number lower bound. All right, so here we are over at my MATLAB script to actually do the calculation. And this first part of the script is just to do a proof of concept and a quick run through of actually counting the permutations themselves. And the second script, which I have over here, is going to actually find the God number for us, or at least the lower bound. So this is pretty straightforward to understand here. We just have our inputs for the number of layers, the number of ways they can turn. So that's just generalizing it to any of the twisty puzzles we want to do here. And then right now I have this for a 3x3 cube, but we can of course change the numbers later if we need to. And then just some inputs for the sequence length. And this loop here, don't worry about this too much. This is just figuring out whether or not to divide the factors by 2, because there was just another setting I put in, but I digress. So now this is where the fun stuff is. This is actually constructing the matrix of the specific size that we need depending on the number of moves that we choose to input into the code. And of course you can see the Fibonacci calculation right here, just getting our Fibonacci numbers to actually use as indices for the matrix part. And then this is actually constructing the matrix here for the first part of it, just adding the number of rows we need, and then this part is actually getting all of the positions filled out. So we can, I guess, kind of start this off here. We run this part of the code, so the sequence length, let's just say we choose 5 moves, and we'll just ignore that part. So we have that run now, and now if we display the matrix, I think I just need to run this section. Okay. Now if we display the matrix, we can see here it is down here. Now right now I'm using 1s and 0s instead of the 12s and the 3s that we saw previously. Just ignore that. I'm just doing that because it's just easier to work with things in binary most of the time within programming. So there's all of this, and you can see that it's the same structure that we saw before. This is for 5 moves. And just imagine instead of zeros, we have 12, and instead of ones, we have 3. Same idea. I'm missing out the very first part here, which is going to be all of the 18s as well, but we can add that in the second part. So now this final part of the code is just substituting in all the correct numbers we need. So the 12s go in for the 0, 3s go in for the 1, the first column becomes all 18s, and then we just do the multiplication, division by 2 where needed, and add it all together. So if we finally complete this last section, then we get our final sequence count. In this case, we got 577,368. And that's for 5 moves. And actually, just to show that this does work for the smaller move counts, here it is for 3 moves. Oops. I guess I must have accidentally clicked it twice. There we go. For 3 moves, we do indeed get 3,240, which we saw earlier for the 3x3 cube. And then for 4 moves, we get that 43,254 that we also saw earlier. So it's exactly the same numbers, so we know this code is working correctly. So now we go over to the code needed to find the God's number. So this is almost exactly the same, except what I've done here is I'm adding another loop to the actual program that's calculating all the stuff. So all this is doing is just doing this and iterating through each choice for n. So n is the number of moves that we're checking. So we're just iterating through each choice of n. This t here is the total permutation count. So as we go through 1 move, 2 move, 3 moves, and so forth, we're actually adding up all of the answers that we get to get the total number of permutations we have passed through. And we can see that at the end here, just adding up all that stuff. And then this last conditional here is to say that if that total exceeds the number of permutations of the puzzle, then we're going to break and just display that final move count. So very simple. So a quick side note, if we first run this code for the regular 3x3 cube, we enter in 6 total layers and 3 possible directions for each layer, and then type in the total number of permutations for the Rubik's Cube, which we all know is 43 quintillion. We get a final answer for the lower bound of God's number as 18 moves. So 1 move better than the naive 17 calculation that we did at the very beginning, if you even remember that. Which is actually really good in this game. You know, because the permutation counts grow exponentially, being able to improve the lower bound by even just 1 move is quite significant. So there you go. This proves that using this more logical method of doing it is better than just the simple logarithm formula that we showed at the beginning. Alright, now on to the FTO. So now we just run this code. And so now let's choose the number of layers on our puzzle. So in this case, we'll choose for the FTO, we're going to choose that we have 8 total layers, and then we have 2 possible directions for each layer. And finally, the total number of permutations for the FTO. This is actually calculable, just as similarly to the 3x3 cube, and it actually turns out that for the FTO, it's 31.4 sextillion combinations. That's right, 3.14 times 10 to the 22 pi, which is actually pretty cool. But anyways, so we have this total number of permutations, and then finally, when we run that whole thing, we get the final answer for the lower bound is 21 moves. And there it is. So that is the actual calculation, giving us that final answer of 21, and we can just double check this by checking the total amount, and we can see that this number does in fact exceed the 3.1 times 10 to the 22 number. So this number is bigger, so it means that 21 moves are required for some positions of the puzzle. Now there might be other positions that require more moves, but we know that in order to be able to reach the entire state space, we have to use at least 21 moves. So there you go. There's the proof. So with that, we now know for a fact that the God's number for the face-turning octahedron is greater than or equal to 21 moves. It's great to finally have some consolation and some idea of a better estimate for where the God's number actually lies for this puzzle. Sadly, at the moment, I'm not aware of an upper bound on the God's number. That is, we don't know that every position can be solved in at most X amount of moves, but it could be less. Well, we don't actually have a number for that yet as far as I'm aware, and it would be nice to get that number as well, and it is something I want to work on in the future, but for now, I'm pretty satisfied with this. So, I hope all of you enjoyed this video. It was a lot of fun to make, and it was really fun to also go through and do all of this research on my own discover all of these great new things and finally apply them to further our knowledge of twisty puzzles in general. I'm sure I'm not the first person to come up with this whole concept of doing the logical network and the recurrence relations to determine all the other products for determining the permutation counts. Again, I'm sure I'm not the first person to do that, but I haven't really seen it published anywhere publicly, at least on forums or on the internet much, so it is great that I'm finally able to bring this out to show to a more mainstream audience. So with that, I hope you all enjoy, stay safe, and thanks for watching.